Hey everyone, let's get started. Excuse me. So our next speaker is Ewelina Hankiewicz from University of Würzburg, and she'll talk about unconventional superconductivity in topological insulators and Rashba 2 DAGs.
So thank you very much for this very nice introduction, and I would love to thank organizers, especially Carlos and Tiaro, to have me here. It's really very nice location, very interesting conference. I learn a lot of things, so it's really nice to be here. So I would like to talk a little bit about actually 2D surface of three-dimensional topological insulator, how the superconductivity comes out over there, and then I actually switch to the Rashba two-dimensional electron gas, because I believe that this is a new platform which might be actually very fascinating, very interesting from the perspective of new platform for finding Majorana fermions. Okay, so let me just go through my outline briefly. So obviously, in the topological insulators, when there is time reversal symmetry, I would prefer to call it topological Andreev bound state, but I call it here Majorana fermion. So just generally in topological insulators, which are proximatized with a superconductor, so we heard about proximity-induced effect already from Igor a little bit yesterday. And I will actually start with the topological insulator, explain you a little bit where are the problems and where is hopefully a hope. So I actually would like to convince you that if you have a phase-dependent thermal conductance, this is what we actually work now with Francesco Giasotto in Pisa, it might be a much better way to detect some of the topological Andreev bound states. And finally, I wanted to say some things about this phase-dependent Josephson junctions on two-dimensional electron gas with Rashba, and John made a fantastic introduction to all of this Rashba and Dresselhaus interaction, so I also go through this quite quickly. Okay, so let's see. Good. So I just did this for students very briefly. You heard from Stefan Stock, very nice introduction to the quantum spin Hall effect and 2D topological insulators. So in Würzburg, we are very much interested in mercury telluride quantum wells. So what happened over there is that usually you have something which has a normal band structure, let's say cadmium telluride or vacuum. So the S-like electrons are building conduction band, and the P-like the heavy hole band, and then you actually put close to this something with the inverted band structure where the P electrons are forming conduction band, and then when you connect these two band structures, then you can expect that something weird happens at the boundary. This was first actually analyzed already by Pankratov in 1980s. That some kind of gapless states can appear at the boundary. And indeed, something appears, and as we found out a good few years later, actually, it can be topological, as we discussed during this workshop as well. So what I call 2D topological insulator, it has a bulk cap, and then it has one-dimensional edge states just at the boundary. And they are spin polarized, as we can see here. So let's see, I'm going in the wrong direction. So let's try. Okay, so similarly, the 3D topological insulators, now I have a three-dimensional system, but I have a surface, which is again metallic surface, which has this kind of spin momentum locking. So here it's important that it's not like in graphene that we are talking about pseudo spin. Here we actually talk about real spin, and the sigma matrix describes real spin, which is coupled here to the momentum. And again, what's interesting here and what will be important for the superconducting state when we actually put S-wave superconductor on this surface state of 3D topological insulator is that there is lack of backscattering. So what happens is that if I, for example, I am at this place at my Fermi surface. Yeah? So let's say this is my Dirac cone, and I am actually looking over here. So I cannot really easily backscatter unless I have a magnetic impurities or something which allows me to flip the spin from this part of the Fermi surface to this part. And the reason obviously is that if I change P to the minus P, I also have to change spin to the minus spin. And that's exactly why this kind of backscattering is forbidden. And this lack of this backscattering has actually fundamental importance for the superconducting properties when we put the S-wave superconductor on the surface of 3D topological insulator, which exactly has the spin momentum locking as we discussed. Okay, so let's go here. Okay, so what happens is that, let me now quickly remind you the Fu and Kane paper, and then a little bit generalize it, so maybe actually emphasize that this is not so simple. So we all would like to have immediately P-wave superconductivity when we put S-wave superconductor on the surface state of topological insulators. That's not true. The first thing is because there is time reversal symmetry in a system. And the second thing is because the spin rotational symmetry is broken. So what happens is that one has actually a mixture of S and Px plus minus IPy superconductivity in this material. Okay, so what happens is I just wrote here Bogolyubov-Dejean equation. So I am working now instead of with the Cooper pairs with the quasi-particles. And what happens is that I have a surface state, obviously Hamiltonian. Then I have a singlet, induced singlet here, and some kind of tunneling as well, chemical potential. So just let's do this. So at the end of the day, if I just look at the correlations, I get exactly mixed S-wave and P-wave correlations. And if I look at my Green function, then I have actually two, or in the Green function of related to the superconductivity, or to the condensate, I have actually two terms. So one term which is related to the singlet, and one term which is exactly related to this helicity. So this helicity which we actually saw in this kind of sigma dot p in the normal states now comes in the correlation function. So what we can expect is that there will be some kind of unusual property related to it. And obviously, that's exactly happens. So if we now, for example, look at the Andreev bond states in the Josephson junctions, which are based on the 3D topological insulator, and we look at the surface state, then in general, we obviously can have exchange Cooper pairs into quasi-electron, quasi-hole. We can find this Andreev bond state. And interestingly, however, because we have this mixed S and P wave, and if we just look at the first component of for kx equal, or for ky equals 0, so for the first mode, which is actually in this kind of structures, we already get something unusual. Huh? So this was exactly done with Grigory Tkachov, and what we name it is superconducting Clan tunneling, because what happens is that you are having actually tunneling of electrons from the superconductor through the normal regime, and we put over the barrier to the second superconductor. And now if I have a situation that I only have, if I have Py equals 0, if I have only a first mode, what happens is that I don't have a Fermi surface to actually backscatter. So I started with sigma x kx, and then I am going to the barrier. But in general, similarly as in the normal states, as we discussed 2 minutes ago, if I change momentum to the minus momentum, I would need to change sigma to the minus sigma, but the time reversal symmetry doesn't allow me. So this is a simplistic picture why the transmission independent of the barrier, which is in the normal regime, should be equal to 1. And this is exactly what you can see here, that if theta is actually, if I am going exactly perpendicular to the barrier, then transmission independently, how large is z, and z is a barrier, is actually equal to 1. And that's interesting fact, which obviously one would like to now use. So one would like to use this barrier to actually see this kind of P-wave component, or this helical component of the superconductivity in these materials. And indeed, what happens is that the first mode, which we just discussed, is 4-pi periodic. And it's just 4-pi periodic because of nature, which is related to this topological Andreev bound state. And what happens is that actually this part of energy spectrum as a function of phase is related to the other part by the time reversal symmetry here, as well as by the helicity in this particular situation. But this is only for the angle which is perpendicular to the barrier. Yeah? So any other angle which I would have here, any other angle theta, which is oblique and so on, would give me actually the 2-pi or gapped states. So I am really having a big problem, yeah? So I have one state, or almost one state, exponentially decaying, yeah? So which would give me 4-pi periodicity, and many states which more or less have 2-pi periodicity, and I am not interested in with. Yeah? So I have to do something to extract this information about the topological superconductivity. And one way to do this, which we did already some time ago, is actually to look at the supercurrent, and that's exactly the formula. So for the superconducting normal superconducting junction, what happens is that D here is a transparency of the junction. Yeah, so you can see that if D is actually going to 0, so if the junction is not transparent, then in the usual ballistic junctions, let's say on the aluminium related to some kind of normal material, which is not related to the topological insulator, what would happen is that my energy spectrum would go to the delta. So it's actually my Andreev bound state would move to the boundary of a gap. But that's very different from this superconducting TI superconducting junctions that where independently how large is the barrier, I actually get a finite energy. And then if I just calculate a supercurrent, which is derivative of this energy in respect to the phase, I still get a non-zero signal. So what will happen is that actually, as a function of the barrier, I expect a finite supercurrent. I also expect non-sinusoidal current phase relation, which, for example, was measured in this paper by Katrin Mola. But I wanted to go further, because as you can see, historically, this is a long time ago. So the question is now, it all looks good. You can say, okay, I can see some signature of this topological Andreev bound states, but we all know that in these materials, there is quasi-particle poisoning, for example. Yeah, so I might not be necessarily going 4-pi. I might actually change a branch, for example, because of the quasi-particle poisoning in my system. So is there another method which actually allows me to go around it and see this kind of topological Andreev bound states beyond what I can see in the current phase relations? And that's exactly what is the second part of the talk. So it's just showing that what I personally believe what might be interesting is actually something which is very unusual. And you should, all students should shout on me now, because what I wanted to do is to do thermal conductance through the superconductor. Yeah? So we know that if I am actually looking at the thermal conductance of a superconductor, should be 0 because it's dissipationless. But I can still get something, okay? Otherwise, I would not be talking about it, okay? So what actually was shown already in, I think, 50s, 60s is that for the usual Josephson junctions, is that although, indeed, through the gap, if I am looking at the transport through the superconducting gap, then I see nothing. But what I can do is I actually can still get an information about the phase. And through the quasi-particles above the superconducting gap, I can also get an information about the density of states through this kind of Josephson junctions. So that's exactly the idea. So what we are doing here, we put a finite temperature gradient, yeah, between two superconductors. And now we wanted actually to calculate a thermal conductance, phase-dependent thermal conductance. So we need an obviously, you can see we are integrating the states not inside of a gap, but from the delta to the infinity, so outside of a gap. So the idea is that thermal excitation is exciting Cooper pairs, so we know about the phase. And obviously, we are looking at the quasi-particles above a gap, so we also know about the quasi-particles and density of states. And okay, and that's actually is like indirect measurements of what's going on in the gap. Yeah? So what's going on with this Andreev, topological Andreev state? Okay, so let's see what happens. So you need to remember is that density of states is really usually normalized. Yeah? So if I am taking some density of states and I have it some Andreev bound state in the superconducting gap, usually this means that something has to happen also to the quasi-particle density of states above the gap because it's normalized. So that's actually what interestingly happens here. So the left is actually density of states, and this is omega, so energy in the units of superconducting gap as a function of the phase. And Z is a large barrier. And then I do the same for the SNS junction. So as I mentioned before already, when we discussed just 2 minutes ago, that if I have a large barrier for a normal junction, ballistic junction, which is not topological, then this Andreev states as a function of barrier will start to go to the edge of the superconducting gap. And because it's going to the edge of the superconducting gap, it's again renormalizing the density of states. And what happens is that I actually get close to the gap, the maximum of the density of states. This is very different from the situation when I have this topological Andreev bound state. Now, instead of this, what happens is that I am taking away, because I have actually this, even for a large barrier, I have this protecting crossing. Yeah? So in general, although as you can see, you can ask me later, but I mean, what happens is I'm in some sense taking this density of states in the gap, or I have it in a gap, and then I'm removing this outside of a gap. And this gives me a very different dependence of the thermal conductance as a function of phase in both of this situation. So even for the 3D topological insulators, that's what we actually checked, when I have a few good modes in the system, let's say 1,000, so there is additional geometrical factor which we found, which actually always gives me minimum in the thermal conductance as a function of the phase. This is very different to the situation, so we need a tunneling junction, Josephson junction, and then we should actually see the minimum. While for the usual junctions, which are related to aluminum and parabolic dispersion normal material, I actually would go from the situation of the minimum when I do not have a barrier to the situation of a maximum if I have a tunnel barrier in these materials. So this should be, because of this density of states renormalization, much stronger signature of seeing this topological Andreev bound state. And we actually did some estimates what could be measured or what kind of gradient of temperature you could measure. So what happens is that we propose the squid. Similar squids were actually done for the usual materials, so materials, the Josephson junctions on the system with parabolic dispersion. And you actually can see is that if we apply the gradient of the temperature to the normal leads, and we have changed the phase difference by the flux here, and we actually take into account the coupling to the phonon bath, then what happens is that the change of the thermal or the flow of the heat from left to the right is related to the thermal conductance and the difference of the temperature between these two left and right reservoirs. And what happens is that if the left reservoirs, let's say, have 500 millikelvin, we actually estimated that the right should have a difference or fluctuation between minimum and maximum 20, 30 millikelvin. You tell me this is very small. Why should I be excited? So actually, from what I understand, talking with the experimentalists, they can measure even 100 microkelvins, at least in Pisa. And I think they are quite excited to actually look at this kind of proposal. Okay. So now we also went further, and now we are having all possible things, which I'm not going to discuss because of time scale. We have actually thermal switches and many different devices, which one can now do on the topological insulators just using this Josephson junctions principles. Okay. So instead of this, let me just focus on the other part, which is related to this phase-dependent Josephson junctions on 2 decks with Rashba, and a little bit explain why we are so excited about this new platform. So, okay, so this is actually Benny Scharf, and he was mentioned already here a few times. So, as you can see here, what we have is very similar setup. However, now we do not have a topological insulator, we just really have a 2D material, let's say quantum well with strong spin-orbit interaction, let's say of Rashba type. And what happens is, obviously, we have some superconductors, as you can see here. We might have some potential, gate potential over here, and we also need a magnetic field. Okay? And why we need a magnetic field, let's discuss this in a moment. Okay, so there are other papers which are related. So in the same nature, actually, was the paper by Charlie Marcus when they look at the indium arsenide quantum well, which was proximatized with aluminum. There are also a few papers already online which are related to Igor and to Alex, where they again have aluminum indium arsenide. I understand that Alex will talk about it more also on Friday. So let me just talk about the system which we looked at. Okay, so why we are so excited about this two-dimensional materials, or Rashba, 2-dex here, in this context? Well, because as you know very well, so far there are lots of experiments which are very beautiful, which are related to the wires. Yeah? So you have semiconducting wires, you have proximity-induced S-wave superconductivity, and you have the spin orbit field, which is perpendicular to the field which is applied. Yeah? So that's usual situation. Now, obviously, in this kind of setups, it's very difficult to put flux, for example, right? Because this is one-dimensional system. So this is different from what we obviously have here, because here very easily in this 2-deck we can put, for example, flux. So that's one of the advantages. Now, another advantage is that, as you will see in a moment, so all of these things concerning, maybe I didn't say this specifically, topological insulator, we usually have to tune the phase to the phase difference of pi, yeah? Because then we have a zero energy crossing, which is exactly related to the particles equal antiparticles, so to Majorana state. Huh? So in this situation, you will see that I can get the topological phase in a huge regime of parameters. So this is very exciting because you don't need to just go with the chemical potential 10 millectronvolts higher or lower. You will see that as long as you have a Rashba system, you can actually see lots of these effects. Not yet everything, because it's more or less beginning of the field, I would say. Okay. Okay, so what happens is, and there is a few references here which were before us. So if I do not apply magnetic field, okay, so if I do not apply magnetic field and I look at the energy as a function of phase, because now, so before I had only one surface of topological insulator, so I did have no problem with the degeneracy, but now I have a Rashba model, so in general I have double degenerate system. So what happens is that this crossing here, the gray crossing here at pi, is not protected. So I need to do something more. I need to remove this degeneracy. And the way to remove this degeneracy is by putting in play magnetic field. Then what happens is actually I split this point here into two, and I have a red and blue one, and then I actually can show, so one can see that if I take a Rashba and I actually proximatize in this situation with the S-wave superconductor, I will have a D-class superconductivity where I can actually have a different Z number, Chern number, inside of this regime in comparison with outside of this. So in topological regime, I will have something which is non-trivial, obviously, and here, so even Z, and then here, odd, yeah? So that's exactly what happens. Okay. So what is experimental setup? So it's actually doped mercury telluride quantum well, but it's not because we want a 2D topological insulator, but because we want a system which has strong spin-orbit interaction, as we already discussed as well. And what we have is here is actually is a superconductor aluminum, and here is phase diagram. So you can see is that, again, because this crossing is not protected for a zero magnetic field, or zero in-plane magnetic field. So here there is actually a trivial regime, which then, when we increase Zeeman field, actually when Zeeman field is of the order of tau-less energy, then we actually go to the topological phase. And this is my Josephson junction. This is actually the place where I can put out-of-plane magnetic flux. So this is more or less the view of the experimental setup. And then I can apply, for example, or I can look at the dI/dV characteristic by applying a voltage from here to the probe. And obviously I wanted to look at I can move this probe actually, and I could look what's going on in the bulk and on the edge, so we're actually thinking in this direction. But in general, what we wanted to see is dI/dV characteristics, which are related with the flowing of the voltage and currents between the superconductor and the probe. Okay, so what happens here is that, and this is not obvious immediately, so I am changing here this in-plane magnetic field. So this in-plane magnetic field is actually changing my system from the topologically non-trivial to the topologically trivial, as you are seeing in this phase diagram, which is kind of large one. So in this dI/dV characteristics, which were related to the conductance as a function of bias, and this is actually for different phase differences between superconductors. And you can see that I'm going from the minimum in a differential conductance when I have zero in-plane magnetic field to the maximum if I actually get a large magnetic field. And I mean, the question is now what really is going on if we are really seeing Majorana. Okay, so what we did, and obviously here, we have a nice scattering approach, which I am obsessed about to make it much better than it is currently. But I mean, what we plot here is actually data which are found from quant. So we actually make exactly this setup in quant and calculated this differential conductance. And what happens is that indeed, what one can see is that this differential conductance goes from the dip to the peak as if when we increase in-plane magnetic field. And now, again, we're trying to connect this with the existence at the edge of Majorana, but that's not this. What happens is actually what we see, and that's what we also claim in this paper. We actually see the density of states coming, what happened? From actually this Andreev bound states, if you want, or from this topological regime, yeah? Because of this kind of phase diagram here, we see actually the maximum of the density of states when we go from the trivial to the topological regime. And that's exactly what we see. So we can actually calculate, and we did it, all of the density of states related to the Majoranas, and they are delocalized. So they are there, but they are delocalized. So one obviously has to work on the aspect ratio, geometrical aspect ratio, to get more localized Majoranas, find corrected chemical potential, and so on and so on. But another thing which might be also interesting for the guys who are working on this platform on indium arsenide with aluminium is that one can also tune and make as a knob here the situation where one has not only the spin-orbit interaction which is related to Rashba, but also which is related, so in this NSOC here, we have alpha and beta, so we have a Rashba and the Dresselhaus. And this is for a quantum well in the 001 direction. And interestingly enough, we actually find that the moment, so what has to happen is actually the spin-orbit interaction field has to be perpendicular. So the full with Dresselhaus and Rashba has to be perpendicular to the direction of the in-plane magnetic field to get maximum signal. Here actually we plot the topological gap. So how changes topological gap? If the topological gap is large, then obviously we can have localized Majorana, if it's not, and so on. We can play with this, so we have additional knobs, which are, for example, Dresselhaus. There are some very weird points. Some of these points are related to what in some sense John was discussing, so meaning that when this NSOC becomes 0, so alpha is, for example, equal to the minus beta, so then what happens is actually you can completely remove from the phase diagram the places where Majorana can exist, and so on and so on. So there is a lot of physics here, which we try to summarize in this paper. Okay, so since my time is running out, I would like to obviously acknowledge my collaborators, Stanford Group with Katrin Mola, Experimental Group in Würzburg with Lawrence Molenka, PISA Group with Francesco Giasotto, and Harvard Group with Amir Jacobi and Bert Halperin. So I was very happy, and I'm grateful that I could be there as a part of my sabbatical. And obviously, a special acknowledgement comes to my group. And let me summarize. So we actually talked about different possibilities of looking at the topological and ray of one-state Majoranas. And I think that one of the very promising new platform is related indeed to the systems with the spin-orbit interaction, because we know, and we actually worked on this 2DEX with Rashba and Dresselhaus for a while already, so we can now use them in the setups where one could possibly measure some of its Majorana properties. Thank you very much for your attention.
Thank you, Ewelina. Do we have questions?
So I was really curious about we talked about the thermal stuff, but I was thinking about it a little bit more. So when you do this thermal gradient, if you think about it from a slightly different perspective, then there should be an expression where a thermal gradient